questions? Anyone about to come up with questions?
This number 28, you can figure out.
Chapter 6. Which one? 2 kilogram hollow putty.
Yeah, I didn't understand why it wasn't 4. Why was it 2?
All right, so 2 moves at 3 meters per second, slams to a 2 kilogram hollow putty at rest. Show how the speed of the 2 stuck together. All right.
Because I would think it'd be 4 kilograms because they're stuck together. But the answer is right here. That's for everybody.
It should be 4 kilograms.
So, yeah, it's 2 times whatever the mass is. And because so it's the total momentum beforehand, which is mass times velocity, divided by 2 times whatever the mass is. The mass cancels out, and you're left with just half the initial velocity. It is correct there. It is somewhat misleading, especially since it is used for meters and mass.
Did you still come up with the same answer? No. So in that particular problem, 2 kilogram blob going at 3 meters per second, which is assume that's the positive direction. I have another 2 kilogram blob at rest. So the total momentum,
It's 6.
mass times velocity, so I have 6 plus 0. So I have 6 Newton seconds or kilogram meters per second, or make up your own unit. So that's my momentum initially. That's gotta be the momentum finally. It's a perfectly inelastic collision. Putty, one of those key words. It might have even said they stick together, but.
This is please stick together.
Okay, so they're gonna stick together, create something that is 4 kilograms. So this is 4. And after, I have 4 kilograms. And so the final momentum is mass times velocity, final. So that's 4 kilograms times final velocity. So the math problem is basically 6 equals 4v. That's the math problem.
Okay.
Bless you. Other questions?
I was confused on chapter 6, 27. I mean, not 27, sorry, 37.
The 2 automobiles, each with a mass of 1,000 kilograms, that one? Moving at the same speed, 20 meters per second, when they collide and stick together. All right, so obviously you can't solve it yet because we need to know velocity. This is the momentum chapter, it's a vector. So in part A, one's driving north and the other one's driving south. So going with the traditional north is up. So I got 1,000 kilogram blob traveling north at 20 meters per second. I think it was 20. And one going south. Going 20 meters per second. Did you have confusion with A and B, or? Okay. So it is a conservation of momentum problem. So we have to figure out what is the initial momentum, because that helps us figure out what the final momentum is. Well, I know that momentum is mass times velocity. I have two objects. Like you call it mass A and then mass B. Now the trick here is recognizing that we are dealing with vectors. Direction matters. It's a one-dimensional problem, so we can get away with just deciding the positive direction. So it doesn't matter which way you consider positive. Out of habit, make up. So this one has, we'll call A, and that one we'll call B. So it's gonna be 1,000 times 20 plus negative 20. So the 20,000 minus or plus negative 20,000 is equal to. So the total momentum before the collision is 0 Newton seconds. Therefore, that has to be the afterwards. And therefore, since the total momentum is 0, if they collide and stick together, I now have a total mass of 2,000 kilograms. How fast does it need to be going so that the total momentum is 0? Yeah, it has to be at rest. So for part A, it's just they're not going anywhere. They stop. You can get into some formal notation, but in essence, it asks for speed and direction. It stops in whatever direction you feel like. B is the trickier one. One car driving north, one east, as shown on page 102. Make sure my, yeah. Now, because the masses are the same and the speeds are the same, there's no preference that one's going to have over the other. So 1,000 kilograms going east at 20 meters per second. Again, so north and east. And then 1,000 kilograms traveling north at 20 meters per second. So what is the initial momentum? And hence, we can't get away with just the positive or negative because it's a two-dimensional problem now. Well, conveniently, it got some unit vectors up there. Initial momentum. 20,000 Newton seconds. E hat plus 20,000 Newton seconds. In hat. Now, the question doesn't ask for what is the momentum, but that if you were asked what is the initial momentum, that's it. Ultimately, we want to know the speed and direction. Well, the direction we can just sort of think through it. That goes back to the fact that same mass, same speed, they're not going to overpower each other. So whatever happens, if they collide and stick together, it's gotta basically go in the direction that halfway in between them. So that one's going this way, that one's going that way, so combined, they would go, that would be a 45-degree angle, or I think as to look towards it, northeast. So if you just use northeast as a direction, then I'm assuming that is split right down the middle of that first quadrant. How fast? There are two ways of going about it, depending upon at which point you want to use the Pythagorean theorem. So let's find velocity first, and then find speed, and then we will do it the other way. What is the final momentum?
The actual momentum.
Yes, right there. So I got 20,000 E hat plus 20,000 N hat. And that's gotta be equal to the final mass times the final velocity. What is the final mass?
2,000.
Yeah, I hope so, if they're sticking together. If it's not 2,000 kilograms, then either the problem lied to you, or it's a lot more complex than what they initially established. So that's gonna be equal to 2,000 times my final. If I'm trying to find final velocity, what would I do? By
2,000.
I divide both sides by 2,000. Now, the biggest mistake I see students make at this point is they'll divide one of them by 2,000 and leave the other one alone. You're dividing that by 2,000 and that by 2,000. So you're left with 10 east plus 20 north is the final velocity. Oop, that's bad math. There should be 10 there. Now the question is asking for speed, so now I have a velocity in parts. How do I find the speed? This is a chance for all of you to say it in unison. It's going to be incredible. 3, 2, 1. No one is brave enough. Suppose I did it this way. I have 10 meters per second east plus 10 meters per second north. And I want to figure out what the magnitude of the sum is. How would you do it? If you want me to hear you, you've got to be louder.
A squared plus B squared equals C squared.
Otherwise known as,
Pythagorean theorem.
oh, I got a little bit of unison there. So 10 squared plus 10 squared is equal to C squared, which is equal to 200. So that's the square root of 200, which is 14.1, something like that. So the final speed, 14.1 meters per second. I was going to do it an alternate way, but
Oh,
I guess Genesis, you started us off on this one. Is that? Do you have a question? Anyone have questions? Doesn't necessarily have to be Genesis.
I just don't understand where you got 28,200 kilograms.
That's the other way.
Okay.
Then let's do it the other way. The other way is, see, this way we figure out the final velocity and then did Pythagorean theorem. The other way is to figure out the magnitude of the momentum and then divide by the mass. So if we instead had tried to figure out what is the magnitude of the momentum, well, I got 20,000 east, 20,000 north, and I'm trying to figure the magnitude. Pythagorean theorem, and you end up with 28,000 200, whatever's. That is the magnitude of the momentum, which should be the mass times the speed. Notice I dropped the vector symbols. So I have 28,200 is equal to my mass, which is now 2,000, times v, divided by 2,000. Then we get the final speed being 14.1 meters per second. Both acceptable. And then the direction northeast, which we talked about earlier. Questions about the gloriousness that is this problem? You can just feel the excitement just bubbling under the surface, waiting, just going to spring out all at once. All right, other questions? Ashlyn, is there a part that you need me to, it looks like you're struggling to see through people.
No, I'm just trying to look.
Okay. Yes?
I think it's number 45 on chapter 7. I think I remember.
Nellie Newton applies a force of 50 newtons to the end of the lever, which is moved a certain distance. If the other end of the lever moves 1/3 as far, show that the force is 100 newtons. Okay. Specific question or just in general?
Just in general.
All right, so this is basically a conservation of energy thing. If I put energy into a system, the most amount of energy that can come out is the same. Now, when we get into thermodynamics, we'll talk about how that is not quite right, but for right now, it works. So, energy in equals energy out. Well, you can put energy into a system by doing work. So I've got this lever here, I'm gonna push on the lever, and I'm gonna apply 50 newtons times how far I push it. Now, they don't specify how far you push it, so I'm just gonna make up a number. I'm gonna say you push it 3 meters. On the other end, force is going to be applied. So I've got a lever here. Let's see. So I would or something like that. So I'm pushing here with 50 newtons of force. And it's going to go down 3 meters. And this side is going to go up a certain distance. It's going to go up 1/3 as much, which is 1 meter. And how much force would it apply? So again, if it's applying a force over 1 meter, then that should be equal to whatever force that is times 1 meter. And so the force, 150 newtons. That's basically what's happening there. I chose 3 and 1. It doesn't have to be 3 and 1. Just so long as this is 3 times that, you'll still get the same answer. Other questions?
I had a question, for it was chapter 7, 39.
Show that 2.5 million joule change in kinetic energy occurs for an airplane that is moved 500 meters in takeoff by a sustained force of 5,000 newtons. So this is the work. I know that the total work done on an object is equal to the change in kinetic energy. Let's look at the specifics here. So they tell us the change in kinetic energy, and we just have to show that equals the same as the work done. We are assuming that, a very simple case, just assume that it's in takeoff, but that's the 500 meters is sort of horizontal. Because I don't want to have to get into what work is being done by the force of gravity, what work is being done by the normal force, etc. All right, so this would be, well, work is force times displacement, which is equal to 20. And so the force that's being applied is 5,000 newtons times the displacement, presumably in the same direction, which is 500 meters. And just multiply 500 times 5,000, and presumably, you get 25 and 5 zeros, yeah. Check it. Other questions?
Yes, it's coming.
I don't remember what question it was, but it was like pertaining to work, and it asked about something about like when it comes to rest, and the answer was just the same. I might have.
So that'd be chapter 7.
Chapter 7.